Okay, in this lecture, I'm going to go over how to complete the Unit 4 practice exam file. So I'm going to go ahead and share my screen with you. So you've got this file, and there's a lot of stuff that I've already done. If you haven't already done this, you can go ahead and do that. But this is going to kind of go through everything that we're doing so far. I'm going to go through Boston, and then I'm going to go through some of these questions down here. And so we'll just go through at least one example of each type of question. Yeah. First of all, from the average salary uh, of job type in each major city. So we're going to go to data. We have average salary by job type in each of the 10 major cities. So there we go, complete this information. So there's a few ways to do this. But the best way to do this, you can go and you're like, hey, I need to do the range, standard deviation, so on and so forth. And you can do all these individually by hand, but what I would suggest is that you complete them by doing the data analysis tool. So I'm going to do the data analysis tool, and I'm going to go data and click right here, and then I'm going to do data analysis, and I'm going to come right up here to descriptive statistics, press OK. And I'm going to do the input range, and I'm going to do Atlanta all the way down to Washington, D.C., and going all the way down. So I highlighted all of the data for all of the cities. And then I'm going to do labels in the first row because I've got the label in the first row of all the cities. Then the output range, where do I want this? I'm going to put it right here, unit 1 through 3 questions. Over here, I'm going to put it in Q2. And then I'm going to say, hey, I want summary statistics and I want a confidence level for the mean. You really don't need the confidence level for the mean, but I just have a habit of doing it. And so it should look like this, and I press OK. And so now we've got the mean, standard error, so on and so forth. And so all this information are all the descriptive statistics, which unit 1 is all about descriptive statistics. So for Boston, what descriptive statistics do I need? Well, let's see here. I need all of these. And so let's see here. Boston, I'm going to do the range, Control C, Control V, standard deviation. This is the standard error, and I don't want that. So standard deviation, Control C, number of upper outliers. We can't do that one yet. Q3. Okay, it's got the mode. Is there a mode? Mode. Ooh, there is a mode. Control C. A lot of times there's not going to be a mode. What's the mean? Control C. The median. And then the standard error, which is right here. And the population mean. The population mean is going to be on the other page. And so the population mean is going to be right here, Control C, and we'll put it right there again. And I'm just going to copy this and bring it back to Boston. But we don't have everything. Let's see here. We still have a few things that we need. So we have the number of upper outliers, upper outlier limit, Q3, and basically everything that's associated with quartiles. And so we're going to go ahead and do that. Let's see. Less than lower outlier limit. Okay, so the number of lower outliers, so anything that has to do with outliers and then also sampling error, we don't have. So the first thing that we need to do is find the quartiles. Now there's a few ways to find the quartiles. Quartile 1 and quartile 3, those are the values that we need. There is this Excel formula, this quartile.exe, quartile.exe, and then you can be like, hey, highlight the data and give me the first quartile or the third quartile. The other option that you have is if you go to the data, you can make a go to Boston, highlight all of Boston, and do insert, and we're going to do a box and whisker. So we've got a box and whisker for Boston, and we don't have, let's see, home, sorry, we want chart design, add chart element, data labels on the left. And so we've got for Q3 and Q1, for Q3 is 77,824.25. And then for Q1, it is 55,413. Okay. And so I'm going to copy this and put it right into here. And copy, Control C, okay, and Control C, and we'll just delete that. So now what do I need to do? I need to do the kind of like this better, maybe. There we go. The formula is on the right-hand side, so you can see what it is that we're doing. And so lower outlier limit, upper outlier limit. Let's do the upper outlier limit. Notice we've got the formula for the upper outlier limit right there. And so what it's going to be is equals the third quartile value plus the interquartile range, which is going to be Q1 minus, or sorry, Q3 minus Q1. And then multiplied by 1.5. Okay, so we've got the third quartile plus the interquartile range multiplied by 1.5, which gives us the upper outlier limit. So anything above this value right here is going to be an upper outlier. Now, what about the lower outlier limit? Equals basically the exact same thing. You can literally copy this and we'll just adjust it. Okay, but instead of D7, we're going to say the lower outlier minus, sorry, the lower, so quartile 1. So this is quartile 1 minus the interquartile range multiplied by 1.5. So we've got the lower outlier limit and the upper outlier limit. Now the question is how many outliers are there above and how many outliers are there below? And so in order to do that, we're going to do a COUNTIF function. So equals COUNTIF, and then you highlight the range that you want to count the data from. And so we're going to go to Boston and highlight all of Boston. So I did Control Shift down or Command Shift down, and I did comma, and then you do in quotation marks greater than, and it's going to be greater than the upper outlier limit. Oops. Greater than and, sorry, it says greater than and then do the upper outlier limit. And this will tell you, hey, we've got a total of 6 outliers above. How many outliers do we have below? Equals, same thing, COUNTIF, highlight the range. So go to data, highlight all of Boston again. Except don't include Boston, just everything below. Okay, comma, in quotation marks, and, oh, sorry, not and, less than, and then do the and symbol. And then we're going to do the lower outlier limit. So I'm going to go back to here and then do the lower outlier limit and close it off. And we see that there's 0 outliers below. Okay, now, how do you get the sampling error? Here, let's make this. How do you get the sampling error? Sampling error is just simply equals the sample mean. So we've got the mean right here, minus the population mean. And that gives you the sampling mean, or sampling error. So we've got the sampling error, and we've also got the sampling error for that as well. But we've got the sampling error for that, and you guys can go through and finish all the rest of these as well. But you've got Atlanta and Boston to look at. Right for that. So yeah, uh, so you've got all of the descriptive statistics for Boston, and that's pretty much unit 1. Okay. And so for unit 2, let's see here. I want to insert. Okay. So remember, there were a total of 5 different distributions that we used in unit 2: binomial, normal, discrete, uniform, and standard normal. And each one of these is used for a different purpose. So we're going to look at just a few of these and do some practice problems here. So for some of y'all, we did this in class, but after becoming a registered nurse, you should expect your salary to randomly be anywhere between 67,260 and 119,646. So what type of distribution should I use to solve this? Well, look at the information that we have. There's a keyword here, and the keyword that we have is randomly, and it's between a max and min. And that right there is when you have randomly dispersed data between a maximum and a minimum value, that's going to be a uniform distribution. So what is the max salary? Should just say salary. Max salary. And the max salary is going to be 119, or sorry, yeah, $119,646. And the minimum salary is going to be 67,260. Okay. So what's the range? You just have to do equals max minus min. Okay. And then what's the average salary? We're going to do equals max plus min divided by 2. Except make sure that you get the parentheses in there. But that is how you calculate the average for a uniform. Max plus min divided by 2. And that gives you the average. And then what's the probability of having a salary over 100,000? Well, in order to do that, we first need to find the height of the distribution. We have the range of the distribution, but what's the height of the distribution? The height of the distribution is going to be 1 over the range, because 1 equals 1 divided by the range. So we've got the height of the distribution right here, which is very small, but when you multiply the height of the distribution by the range of the distribution, it gives you 1. So equals height multiplied by the range, it gives you 1. So even though it's a very short height, this is the probability of any one given dollar outcome. So if I were to say, what is the probability of having exactly $100,000 salary, it would be that. Okay, so what is the probability of having a salary over $100,000? Well, in order to do that, we need to find the between 119,646 and 100,000. So equals 1, or we can do equals minus 100 multiplied by the height. Okay. Multiplied by height. Okay. And I should have put these in the opposite or control C. There we go. I should have put height first. I don't know why I didn't. Times. There we go. So we've got 37.5% ish, and that's the height of the distribution, then what's the probability of having a salary of less than 75,000? Once again, selection times height. So we're going to do equals 75 minus the minimum value, which is right here, times the height of the distribution. So it's going to be about 14.77%. Then what's the probability of having a salary between 75,000 and 100,000? Same thing. Equals minus 75 times the height. And so you've got the probabilities of everything right there. Okay, so right here, this is something that I just put in here. Let's start by coming over here. This right here is Unit 2. This I took from the discrete tab from the Unit 2 Excel document, and I just adjusted these just a little bit. So we're going to put the midpoint, the probability, so on and so forth, all right here. So the first thing that we need is we need the midpoint. We need the midpoint of each of these classes. So we're going to do equals the lower limit, or the lower limit plus the upper limit. And then we're going to divide it by 2. And that gives us the midpoint of that class, and we're going to drag it all the way down. Now what we need is what's the probability of getting a value between here and here? In order to get that, we need the relative frequency. So we took a sample of how many ever this is. Let's find out. 1,791. Okay, so for this next question, we're looking at right here, a survey of job salaries for 122 different occupations in Atlanta indicates the following median salaries for the jobs. It is broken up into 8 classes with varied frequencies in each class. So looking straight over here, we've got these all these different these medium job salaries, and they are in these classes right here. And so we're like, hey, what is this distribution? And so you've got 8 different classes and random, seemingly just different amounts in each class. So because of that, the formatting, and because there's just different frequencies that seem to not follow any pattern in any class, we know that it is a discrete distribution. And these are all discrete classes. This is a discrete class, this is a discrete class. In other words, what's in this class can't also be in this class. There's no overlap at all. Okay, so coming over here, I took this right here from the Unit 2 Excel document. And so this is something that you might want to have on your Unit 2 formula sheet. Sorry. And so we're looking right here, equals, and what we need to do is we need to find the midpoint. And so you've got the midpoint of all these classes, and we're going to use this discrete probability distribution template, if you will, to calculate the variance, standard deviation, and all sorts of information. So equals the midpoint. And so we're going to do the lower limit plus the upper limit divided by 2, lower limit plus upper limit divided by 2. Now, it's very important here. I did this incorrectly, and I did that on purpose because I want to make sure that you guys know, make sure that you get those parentheses in there. Okay, so we're going to get those parentheses in there, and I'm going to drag it down. And so now we should be good to go. We've got all the midpoints going all the way down. Next thing that we need is the probability. In order to get the probability, we need to calculate the relative frequency. Okay, the relative frequency is going to be the individual count divided by the total count. Okay, so I've got 4 divided by 122, and I'm going to do the absolute reference sign in front of the 44, so the 44 doesn't move. And I'm going to drag this down. Okay, and so I've got all of these, and just to check, we're going to do equals sum, make sure that every one is accounted for. This should equal 1, and yeah, we're good to go. So I'm going to copy this, Control C, and I'm going to put it under the probability right there. Okay, and now we're going to look at the individual contribution to the mean. So we're going to do equals n multiplied by p. Okay, and then we're going to drag it down. And then when you add all those up together, it's going to equal the mean. So now we've got the mean right there. Now you need to calculate the difference from the mean. So we're going to do equals the value right here, n, minus the mean. And once again, we're going to put the absolute reference sign right there. And then we're going to drag it down. So now we've got the each individual class's difference from the mean. So class difference from the mean. There we go. Then we're going to do equals the difference from the mean squared. Okay. And then equals the probability times the difference from the mean squared. And then we're going to add those all up together. And then we're going to take the square root of it. So when we add those all up together, whoops, equals square root of the variance, sorry. So when we add these all up together, gives us the variance. And then when you take the square root of it, it gives you the standard deviation. So now you have everything that you need to fill in this information right here. So we've got a relative frequency. And so we're going to take the relative frequency. We've got all this information, and let's go ahead and finish this. What's the relative frequency of jobs with salaries between 60,000 and 80,000? So you come right over here, and you've got 60,000 to 80,000. It's just this right here. So we're going to add these together. Equals sum 60,000 to 80,000. And then we're going to put this right here, paste values. Okay. What is the class interval of the last category? So we haven't done class intervals, so let's do that. So class interval is going to be max minus min of the, or upper limit minus lower limit. So let's drag it all the way down. So it says, what is the class interval of the last category? This one right here. And that's going to be 30,000. And it is okay to have these all different like this, because there's not as many over here because the data there, it's kind of skewed. There's some outliers up above, and that's why I've got these categories are just slightly higher or slightly larger. Okay, so what's the class interval of the first category? That's going to be 10,000. And then the frequency of the first category, the actual frequency, that's going to be the count, and that's going to be 4. What is the grouped average salary of all jobs? That's going to be right here, 59,508. And then what's the probability of having a salary under 100,000? So under 100,000, that's going to be all of these. So under 100K equals sum and it's 95% roughly. And paste that. And then what's the standard deviation of salaries? So it's going to be right over here. Control C, paste values. Then what's the probability of having a job with a salary between 70,000 and 100,000? And so that's going to be 70 up to 100. That's right here. Equals sum. So that's going to be 22. Okay, and what's the best chart to display the frequencies of this continuous data? So to display frequencies of continuous data, the best thing to use is going to be a histogram. And so you'd make a category for each one of these, and then for each one of these categories, and then it would you'd be able to display it. So the best way to do that, oh, you could do, yeah, like this. Insert, and then you're gonna actually do a bar chart. Oh, it didn't like it. You would have to make these into a text. Let's see here. It's really not going to like this. Well, let's do this. Paste values, and then we're going to make it text. Insert bar chart. Still doesn't like it. Oh well. Whenever you use numbers as labels, it doesn't like it, and so anyway. But yeah, it would be a bar chart. Or sorry, a histogram. Histogram is what it would be. So this is one that we did in class, or you can do by yourself if you didn't do it in class. And then going on down here, using this information above, right here, Baylor wants 30% or more of their graduates to have salaries of 70,000 or more. They plan to take a survey of 200 graduates. First of all, what is the empirical probability of a job having a salary above 70,000? So in order to do that, we have right here, 70,000. You add all these together. And so equals sum, 70,000 or higher. And that's going to be 26, roughly 26%. Okay. Okay. And so 70. Okay. Then if I survey 200 people, what is the most likely number to have a job, to have jobs above 70K? You do probability of above 70K multiplied by 200. So equals multiplied by 200. So the most likely number is going to be 52. Okay. What is the number of people that would what is the number of people that would need to have salaries above $70,000 or more for the result to be 30% or more of the 200 sample? Okay, so in order to do that, we need to start using the binomial probability distribution. Well, why are we using the binomial probability distribution? That's a great question. Baylor wants to have 30% or more of their graduates to have salaries of 70,000 or more. They plan to take surveys of 200 graduates. The reasons why is you've got two possible outcomes. They're either above 70,000 or below or not. The probability is the same at every trial. So the probability of 26% is the same at every trial. And then they have a fixed number of trials of 200. So we need to determine right here is the probability of success. What is considered a success? And that is salary above 70K, and this is the probability of that. Okay. So, what is the number of people that would need to have salaries above 70K to result in 30% or more of the 20% sample? So literally all that I'm asking is what's 30% of 200? Equals 0.3 times 200. So 60 or more people is the desired number. Um, so what is the probability that 70% of graduates will have less than $70,000? Okay, there's a reason why I'm asking for 70% less. But first of all, once again, what is 70%? 70% is equals 0.7 multiplied by 200. That's 140. So equals binom dot dist, and the number of successes, trials, the probability of success at each trial is going to be 1 minus, and then we're going to put true. Okay. So to be honest, this is a rather difficult question. Probably should have phrased this a little bit differently, but basically what I did here, I'll show you. I ended up making it so that what was considered a success is making less than $70,000 with the way that I did this. And so I was like, hey, 70% of 200 is 140, and then the probability of that is 1 minus the probability of uh less than $70,000 is 1 minus the probability of 70,000 or more. And to be completely honest with you, I won't ask you to do anything this difficult on the exam. Conversely, what is the probability that 30% or more of its graduates will have a salary above $70,000? Okay, so we've got the you can kind of just skip over this one. This is a really difficult question, so just skip it. But this one right here, what is the probability that 30% or more of its graduates will have a salary of above 20 or above $70,000? So we're going to do binom dot dist, and so we're going to do equals binom dot dist dot there's a couple ways to do this, range. And so we've got a total of 200 trials. The probability of success at each trial is right here, and the number of successes is going to be anywhere between so 30% or more, so that would be 141 up to 200 would be 30% or more. And to be frank, this whole question is much harder than what I would actually have you do on an actual exam. So this right here, binom.dist.range, is the probability of it being any value of 30% or more. And so that right there, whoops, number of trials, the probability of success at each trial. Oh, sorry about that. So number of successes, it would actually be not 141, but 61. So this right here, anything more than 60 successes would be, hey, more than 30%. So anything more than 60 successes, which what is a success? Salary above $70,000 is a success. So if we have 61 or more above $70,000, that's what it is. And so it's going to be 0.0908. The other way to do it is with binom.dist. So equals binom.dist, the number of successes. We want 60 successes. The number of trials, 200. The probability of success right here, true. And this right here will give us 60 or less. So if you want 61 or more, you do 1 minus, and it'll give you the same answer. So 1 minus the probability of 60 or less will give you the probability of 61 or more. Once again, this is a very hard question, much harder than what I would actually put on an exam. Okay, what is the probability that between 40 to 80 people will have salaries above $70,000? This one's actually a little bit easier, equals binom.dist.range, and trials 200. Probability of success is right here. The number of successes 40 to 80. And so 98% is the probability there. And then right here, before ever surveying anyone based on the data, I can be 95% confident that less than how many people will have salaries above $70,000. So we're going to do equals binom dot inverse. And then the number of trials is 200. The probability of success. And then I want to be 95% confident, which is either 0.05. Yeah, because if it was 0.95, I am 95% confident that less than 42 people will, nope, it is 95. I'm 95% confident that less than 62 people will have um, there we go. So this is how you should do it. So coming down to here, for jobs in Atlanta below 60,000 with 95% confidence and a sample size of 65, answer the following information. Okay, first of all, jobs in Atlanta, so sample size of 65. What is the point estimate of the population proportion for that city? So calculate the proportion from the table on the next tab, but use the this in the prompt. So the point estimate for jobs in Atlanta below 60,000, we're going to come right over here to Atlanta. And so we've got to find what is the proportion of jobs above 60,000. Is that what it asked for? Below 60,000. Okay. Okay. So equals count if we'll do this whole range, comma, less than, in quotation marks, and 60,000, and then out of how many? 83. So equals 83 divided by the total of 122, and that's 68.33%. So let's go right here. What is the population proportion? Paste value, and it's 68%. What is the point estimate? So what is the T or Z statistic with proportion? We're going to use the Z, so 95% confident. It's going to be 1.96. And then what is the confidence level? And remember, for the Z values, Z for 90% is going to be 1.645. 95% is going to be 1.96. 99% is going to be 2.576. Okay. So what is the confidence interval? The upper limit. Well, what you should do here is if you go to your formula sheet, you can use the confidence, you can use that to determine this, but I'm going to go ahead and open up the Unit 3 workbook, Unit 3 decision tree, which you guys have this. But what are we doing? We're estimating a confidence interval around a population proportion. Okay, so I'm going to come right here and I'm going to say, okay, I'm making a confidence interval around a mean or around a proportion. I'm doing it around a proportion, and I'm going to come right here and I'm going to find a confidence interval around a proportion. And so I'm going to come right here and there we go. What is the confidence interval? Upper limit, lower limit? First of all, we've got the probability or the point estimate of the proportion. And then we've got the Z value, like I said, 1.96. And then we've got E, which is going to be equals the Z value multiplied by the square root of the proportion multiplied by, in parentheses, 1 minus the proportion divided by n, which is 65. So we're going to put 65 right here. And so the margin of error is right here. So equals the proportion plus the margin of error, and equals the proportion minus the margin of error. And so this is the lower limit and the upper limit. So lower limit is going to be 0.56695. And then, what is the upper limit? That is going to be 0.7937. And then the confidence interval is between those two. I really should have put what's the margin of error. And really, here, let's do this. And margin of error is going to be right here, paste the value. Okay. And then what can I communicate about this to the city manager about the respective city? What we can say is we are 95% that the actual population proportion of salaries below 60K is between 56.7% and 79.4%. And so you can kind of just replicate this for all these. And then to be 95% confident with a margin of error of 3%, how many total people would need to be sampled? Once again, we come to this fun little shindig, and we're needing a sample size for confidence interval around a proportion. And so I'm going to put that right here. So to find a sample size, we're going to change a few things. So we want to be 95% confident. So the Z value for 95% is still 1.96. And then the proportion with a 3% margin of error. That's very different than 11% margin of error. And so we're going to change the margin of error to 0.03. The proportion is still the same, which is right here, paste value. Oh, this would have worked. And so the sample size that we need is to just follow along with this, equals the proportion multiplied by 1 minus the proportion, multiplied by the z-score divided by max allowable error, squared. So how large of a sample do I need? I need 929, which is a very different sample size. Okay, remember, always round up. So you can do the same thing going all the way down with all of these. Just put it inside of both of these. And we're good to go. Okay. Now, oh, look at that. Sample mean, sample standard deviation. I gave you all this information right here. And so we've got the same thing, 65, sample size, 210, so on and so forth, going all the way down. So what is the point estimate of the population mean for the city based on the data above? So we've got Atlanta. The sample mean is right here. What is the value of the T or the Z statistic? Well, we're going to be using T right now, unless we have a population standard deviation, which right here, we don't have a population standard deviation. So we've got the sample standard deviation. So in order to get the T value, we're going to do equals T dot inverse dot 2T. And the probability is going to be 0.05. And the degrees of freedom is going to be n minus 1, which is 64. And so that's going to be 1.99. And notice T dot inverse dot 2T is what you need there. And then the margin of error. The margin of error, once again, we're going to come over here to this trusty sheet. And so we've got this margin of error right here. Okay. We're doing a margin of error with the population standard deviation unknown. So margin of error around a mean with population standard deviation unknown. So I'm going to copy this. I'm going to put it right here. Okay. And so how do I calculate the margin of error? First of all, I've got the mean. I've got the sample size. I've got the degrees of freedom, which is 64. The T. Okay. See, it even says it right there. Then right here, what is the standard deviation? Got the standard deviation right here. And then I've got equals standard deviation divided by the square root of the sample size, which is 65. And so that right there is my standard error. And then the T equals t multiplied by the standard error. And then we've got equals for the margin of error percent. So we've got the margin of error. Margin of error percent is margin of error divided by the mean. And then what's the upper and lower limit? Equals the mean plus the margin of error and equals the mean minus the margin of error. Okay, so let's look at this. What is the margin of error? Margin of error, Control C, paste value. What is the percent margin of error? Look at that, I've already got it all ready for you. Percent margin of error, confidence interval upper and lower limit. And then what can I communicate to this about my city manager, about the respective city? I am 95% confident that the actual population average salary is between 54,306.72 and 63,816.83. And then to be 95% confident with a margin of error of 2,500, how many total people would need to be surveyed? So I need to calculate the sample size. So I'm going to do this, needed sample size. So step one, I've got my standard deviation, my sample standard deviation. So we're going to put that right there. Oh, yeah, standard deviation. And then the z-score, I want 1.96. The maximum allowable error is 2,500. And so what's my needed sample size? Equals, in parentheses, the z-score multiplied by the standard deviation divided by the maximum allowable error squared. And that tells me that I need 226.35 or 227 people. And so you can just follow along with that. And I'm probably going to save this and put these over on the right-hand side for you to, work through. Okay. When you're on the actual exam, these are things I'm not going to give you the Excel stuff. So maybe I won't make it available to you. You'll just have to, do it like you would on the exam, put it up there. And follow along from your piece of paper that says, okay, this is what I need to do, this, and this. And so just look at your piece of paper and follow right along with your piece of paper as to what you should do. But you can do all the rest of these for that as well. Now let's look at these hypothesis testing questions. Okay. And so this is more or less what we did in class. I'm just gonna delete these because, yeah. There's a couple classes that didn't get to these. Well, I'll delete all of them. Are the number of job openings by city in 2016 proportionate to the number of job openings by city in 2019? So, are the number of job openings in city in 2016, we're looking at proportionate is one keyword. And then we're looking at 2016 compared to 2019. So that right there is goodness of fit unequal, because you're saying, hey, is one compared to the other? And this one proportion compared to another proportion. And what Taylor tests, this is right, because they're all chi-squared are all goodness of fit are all right. And then null hypothesis. The null hypothesis would be there is no difference in the proportion of number of job openings by city in 2016 compared to number of job openings in 2019. And the alternative is there is a difference in the proportion of number of job openings in 2016 compared to the number of job openings in 2019. Okay, independent variable. To do that, I want to actually get the data. So I'm going to look at job openings, 2016 to 2019. I'm going to copy this, Control C. And that, I already put it in there, but 2016. And then 2019, you would come right here and then you do 2019. And then go to goodness of unequal 2019. And so what is the independent variable? Well, what's the dependent variable? The dependent variable are going to be these values right here. Okay, well, really, it's these values. Okay, so it is the average number of job openings. Independent variable is going to be the city, this right here. Okay, and then you guys can do the rest of this going all the way down. But once again, we already did the null and alternative hypothesis, and we already did, it's a right tail. Okay, and then looking right here, the hypothesis testing question, is the average salary in San Francisco greater than the population salary? Okay, so we have one sample, San Fran, compared to the population. And then the other word is greater. So this right here is going to be single sample because there's only one sample, and it's going to be right tail because it's greater. Now I put some wonderful things right up here. But for a single sample, you are comparing a value to, or you're comparing a sample mean to a sample mean, sorry, you're comparing the mean of San Francisco to the population mean. So we're going to do the null hypothesis is the mean of San Francisco, the mean underscore San Francisco is less than or equal to and then we need to find the actual population mean. 62,000. Let's just do 62,740. Okay. And so that right there is the null hypothesis. The alternative hypothesis is going to be the opposite. The mean of San Francisco is greater than. Oops. And then the independent variable is going to be city, which is the San Francisco. And then the dependent variable is going to be salaries. And the way that we do this is, let's just delete this, pretend that it wasn't there. But we go to the data, get San Francisco, copy this, go to single, paste it, and then we're going to put that up there, get rid of San Francisco, and then get the population data. And put it right there. Okay. And then once again, you see these are the dependent variables, and it's dependent on this. Okay. Next, we have hypothesis testing question. is the average difference in salaries by job type between Chicago and Houston greater than 0? So we've got average difference. And then greater than 0. And then you've got 2 samples. Okay. So 2 samples, average difference greater than 0. The 2 samples and average difference and comparing it to 0 are all indicative of it being a paired samples. Okay. And once again, greater means that it's right tail. And so we're going to do something similar to what we did here. It's very similar to a single sample, but instead of comparing it to the mean, we're comparing it to 0. So we're saying the mean difference is less than or equal to 0, and we'll do the same thing. The mean difference is greater than 0. And so are the number of jobs, is the average difference in salaries by job type between Chicago and Houston greater than 0? Once again, the independent variable is city, because what is the dependent variable? Salaries. Salaries are dependent on city. And so let's look at what this would look like. Data, we've got Chicago and Houston. And we're going to go to independent. Chicago, I'm sorry, not independent, we're going to go to paired. Chicago and Houston. So we just pasted Chicago and Houston right there. And then the data. And what is it paired on? Job category. So you've got Chicago and Houston, and then in order to get the difference score, you do equals Chicago minus Houston, because these two are paired. These are all paired back and forth, left and right. And so you've got the difference score going all the way down, and it's paired on that. And so the average difference, so on and so forth. And you've got the dependent variable down here and the independent variable right here. And it is an upper tail test because you believe that it's going to be greater than 0. Okay. Next, are the number of job openings equally proportionate between cities in the year 2018? Okay, so equally proportionate, and that's going to be goodness will fit equal. Because we're only looking in the year 2018. And it's right tail again, because all chi-squared goodness of fits are going to be right tail. And then the null hypothesis. There is no difference in the proportion of the number of job openings. There is no difference in the proportion between the by city. Okay, and then there is a difference in the proportion of number of job openings by city. So in other words, this one's is saying every single city has the same proportion of jobs, and this one says every city does not have the same number of jobs. So let's look at what this would look like. So let's look at the data. Average number of job openings by city. So we're looking at the year 2018. And we're going to go to goodness of fit equal 2018 job openings, and then data, we are looking at the cities. And so we've got the job openings and we've got the cities. So what is the dependent variable? That's job openings. What are they dependent on? The city. So you've got the independent variable, you've got the dependent variable. City, and then job openings. And once again, there we go. Is the average salary from an accountant different than the average salary of the population? So from average salary by job type in each of the 10 major cities, is the average salary for accountant different than the average salary of the population? So once again, you've got population, average salary for accountants. So what are we going to do? We're going to go to data, go down to accountants. And we've got this right here, Control C. This is a little weird, but we're going to, if you were to go to single sample again, you could paste it like this. And then it's being compared to the population. So leave the national there. And then we'll do data, like the accountants, put it right there. Okay. So that's single sample. And then hypothesis testing. And then different. The word different here. That means, okay, so once again, one sample, population, different. Single, two tail, because the word different gives you two tail. And then the way that you would write it, we're going to do something really similar, except instead of a upper tail test, we're going to do is, and what is this? Accountants. Is not equal to. And then it's going to be the same exact thing as what it was before, city and salaries. Okay. Next, is the median base pay from 2014 to 2016 less than the median base pay from 2017 to 2019? So we've got two samples. And then it really should say, is the average median base pay less than the average? So we've got independent, and it's going to be left tail because it says less than. Okay. And then we're going to do Control C. Median base pay. First. Let's see here. And then it's going to be greater than or equal to the median base pay of the second. And so you've got a sample mean compared to a sample mean. So in other words, the first, which is 2014 to 2016, second, which is 2017 to 2019. So this is how you would write this. This is for an independent sample. You've got a sample mean compared to a sample mean. This right here is single sample, a sample mean compared to a value. And then you've got the mean difference compared to 0 for a paired. And then once again, so then you've got uh salaries. Are dependent on year. Okay. And then are the number of job openings by year in Los Angeles proportionate to the number of job openings by year in New York? This right here is, we're going to do this a little bit differently, but this is going to be proportionate, and it's going to be LA versus New York. Goodness of fit unequal, right? And then we can, it's really similar to this. So we're just going to edit this by year in New York LA. In LA, sorry, LA needs to go first. And New York, because notice how the question is asked. And New York needs to go second. Then same thing. There is a difference. Okay, so I'm going to copy this. We're just going to delete this. And we'll put the information in there. So go to data. We're going to go with LA. And we're going to paste this like this. And New York City. And 2016 to 2019. So LA. And then we're going to do New York. And so you've got that all set up for the goodness of fit unequal. And then right here, you've got the independent variable. Oh, sorry. Yeah, is going to be year. And then it's going to be job openings. And the reason why is because the number of job openings is dependent on the year, which is being compared to the job openings in New York by the year. And then we've got, is the average salary in New York different than the average salary in DC? This is almost the exact same thing as, well, this is a little different from the average salary of by job type in each of the 10 major cities. We've got two samples. Average, or no, is the average salary different? And there's nothing that implies that it's a paired sample at all. So this is independent. And different is two-tail. And so what you would do is come right here, data. What did it ask for? New York and DC. So we're going to do independent. We're going to copy. So independent. New York, DC, and BC. And then you can get everything from there. And I guess I never did the first one. And the first one is literally just comparing the median base pay by year. So we're going to copy that, paste that, and it's all set up to go. Now, the weird thing about this one is if you didn't know it, or if you did know it, these two are actually matched, but that's not what we're asking for. We're asking for the average of New York compared to the average of DC. And that's what the question asks for. So even though if you go to the actual data, you're like, hey, average of New York and DC, you could run a paired. Now, if you could run a paired in the real world, you should. But we're not going to because, there's only so many questions that I can ask from the data that I have. And so that's why I have it set up as an independent, because I said, is the average of New York different than the average of DC? And then, are the average number of job openings in Atlanta equally proportionate by year? And so we're going to do right here, equally proportionate in Atlanta. And that's goodness of fit equal, right? Because they're all right. And then, create copy. And I'll delete this. So data, Atlanta by year, paste, transpose. So I'm going to do goodness of fit equal to, whoops. There we go. Year. So the year is the dependent, sorry, the independent, the job openings is independent. So once again, we've got independent and year. And then we've got right here, the last question. Is the average difference in salaries by job type between Philadelphia and Seattle different than zero? There's is really no different at all than this. So I can literally just copy this, except we're different. So because it's different, the null hypothesis is equal. The alternative hypothesis is not equal. And then this right here is two-tail. Because this is different than zero. Okay. And once again, equally proportionate. I'm going to copy this. And the proportion of job openings in Atlanta and then there is a difference. And then the independent, let's look at that really quick. I'll finish that. Okay, it is two-tail, so equal. And then this is not equal. And what is it comparing? New York and DC. So we'll do New York, and DC. I don't want to put D because that stands for difference. So New York and DC. Um, and then the independent variable is the city, and then the dependent is still salaries. And so, yeah. And so that's how you do all of these. And hopefully this was beneficial to go through. I will try to update um, all the rest of these as I have time. Um, but yeah, that's all the answers for at least one example, and then you guys can do all the rest of these examples uh, and all of these on your own. And yeah, I'd suggest working with your partners, working with your friends, and going from there.